The selection sort is an in-place comparison sorting algorithm. It has an of n squared time complexity, which makes it inefficient on large lists. Generally, it performs worse than similar sorting such as the insertion sort. The selection sort is noted for its simplicity and has a performance advantages over more complicated algorithms in certain situations. So you have an input list of giraffes that you want to sort by the length of their necks. So you take this input list and you divide it into two parts. One part would hold the sorted array of the giraffes' necks, and the other part would hold the unsorted list. So in the beginning, the whole list is unsorted, but you start building up inside this array. This is why it's an in-place sorting algorithm, because it's sorting in place, which means you just swap items inside the array. You don't need really an auxiliary array. So the algorithm divides the input list into two parts: a sorted sublist, you just name it the sorted sublist, and another part which is the unsorted sublist. In the beginning, you only have one array, right? Because you get in the input, I want to selection sort this unsorted array. And the way you do this is that you start iterating through the array. You want now the first item to be sorted. In order for the first item to be sorted throughout the array, you need to find the minimal item. So the basic structure of the algorithm is find the minimal item, put it on the first place. Find the second minimal item, put it on the second place, and so forth. So the selection sorts, it's like emphasizing the selection part of the whole algorithm, because what you're trying to do is to select the minimal item and place it at the tail of the sorted list. So the way selection sort works is that on each sub iteration, it goes through the list, finds the minimal item, put it on the beginning. Okay, so the algorithm divides the input list into two parts: a sorted sublist of items which is built up from the left to the right at the front. So it's from the left of the list, and the sublist of the remaining unsorted items that occupy the rest of the list. Initially, the sorted sublist is empty. And when we refer to the sorted sublist, remember that we refer to the same input list that we got in the input. And the algorithm proceeds by finding the smallest or the largest, depending on the sorting order, if you want to sort from the smallest item or from the largest item. So it finds the smallest element in the unsorted sublist and it exchanges it. It swaps it with the leftmost unsorted element. So it's putting it in a sorting order. So in this way, when you look at the list, it's first unsorted. Then at the end of the first iteration, you would see that the first item is sorted. Then at the end of the second iteration, you would see that the second item is sorted. Then at the end of the third iteration, you would see that the third item is sorted. And the way it works is that because on the first iteration it places the minimal item on the left side, by swapping, by placing it, you just search for the minimal item and put it on the leftmost side. You swap it with the leftmost item. And this we call the sorted array, because we have just split the array. We just found the minimal item and placed it on the leftmost part. So we have a sorted array. The sorted array is the first item, which is the minimal item. Now we need to find the second most minimal item and we place it on the second place of the array. So now we have again two arrays, one unsorted because we only found the most minimal item, and the second most minimal item, placed it on the first two items on the left of the list, and the unsorted, and then you continue like this. Now in each iteration you're trying to find the minimal item, and because in each iteration you're trying to find the minimal item, you would like scan the list n times for each item, n times to find the most minimal, n-1 to find the second most minimal. So you would see that you have an inner loop, like you have a loop inside the loop, which makes it of n squared time complexity. You also have of n squared on the worst case comparisons, and because we are comparing items, so we are like comparing all the items in order to find the most minimal item, but we're comparing them n times. So the time efficiency of the selection sort is quadratic. So there are a number of sorting techniques which have better time complexity than the selection sort. For example, the merge sort or the quick sort. And one thing which distinguishes the selection sort from other sorting algorithms is that it makes the minimum possible number of swaps, n-1 in the worst case, because each time you find the minimal item, you swap it, but you don't do this for non-minimal items. Okay, so you only have n-1 minimal items that you need to swap. Okay. So let's take an example. Let's say that we have as an example an input array list which contains the following 5 numbers to sort. So this is the unsorted sublist: 11, 25, 12, 22, and 64. So the minimal item is 11. Okay, so we leave it on the left side, and now we have one item which is sorted. The next minimal item that we find by scanning all the remaining items is 12. So we swap it with 25. The next minimal item is 22. So we swap it with the next item on the unsorted list, which is 25. And like this, we continue to scan the unsorted array until we manage to have a sorted sublist that contains all the items in the input. If we compare the selection sort to other sorting algorithms, then among all the quadratic sorting algorithms, all the sorting algorithms with a simple average case of O of n squared, then selection sort almost always outperforms bubble sort and insertion sort. After the kth iteration, the first k elements in the array are sorted. So in this way, it's very similar. The insertion sort's advantage is that it only scans as many elements as it needs in order to place the k plus 1 element. So while selection sort needs to scan all the remaining elements because it needs to find the minimal item and to move it to the correct place. However, in simple calculations, we can see that insertion sort will outperform about half as many comparisons. It would need about half as many comparisons as the selection sort would need. Selection sort is preferable to insertion sort in terms of the number of writes or the swaps, because it has often writes, because we do only n-1 swaps. And of course, all the other divide and conquer algorithms such as merge sorts really beat it on large arrays because they are n of n log n. A variant of the selection sort is the heap sort, because also in the heap sort we find the minimal item, but the heap sorts provide us with the ability to immediately find the minimal item, and it's speeding up the finding and also of the removal of the minimal item. So when we implement the heap sort, it's a kind of an improvement over the selection sort, because both in the selection sort and both in the heap sort we are trying to find the minimal item. But in the heap sort we can reorganize the heap in O of log n, and this is instead of O of n that the inner loop has in the selection sort in order to find the minimal item. So in the heap sort, in the general case, you already have the minimal item at the top, but then you need to reorganize and reshuffle the heap, so it's O for log of n. But in the selection sorts, you need to scan all the items in order to find the minimal item, so it's O of n. And therefore, in the heap sort, it's O of n log n, because for each item, we take the minimal item, and we do this in n iterations. So you can just look at the heap sort as an enhanced selection sort. And with that, we have finished our quick discussion of selection sort and comparing it to other sorting algorithms, to the heap sort, to merge sort. To summarize it up, it's a right efficient sort because we do only O of n swaps. However, the number of comparisons is quadratic. It's O of n squared. the number of swaps is low. The number of conversions we do is again often squared, and we don't really need new memory because we do this in place. We basically split the array into two cases. One is sorted and another one is not sorted. Every iteration we find the minimal item and we swap it with the current with the current place of the array. We swap with the first item, then we swap with the second item, then we swap with the third item, and in this way we build up gradually in a way which is sorted.